All right, so this time we're going to continue talking about fluids, and we're going to talk about specifically Archimedes' principle. So, first thing I want to do is remind you of a couple of things. Density, rho, is defined as mass over volume. We're going to need that. It's going to be important. And pressure was force per area. And these two variables are important when talking about fluids, and they'll continue to be important. So, to get into Archimedes' principle, let's think about one of the main equations we had, which was how much pressure an object feels when it's at some depth. So if we have some kind of a container with some fluid in it, and there's an object, and we say, okay, this object is placed 2 meters down from the surface, then we could say the pressure felt by the object at this depth is rho times g times h, where h is this depth, of course. And so the deeper you go into the fluid, the more pressure you're going to feel because you're at a higher depth. But let's look at this a little bit more in detail. And so if we have our container, the fluid, and we've got an object, let's say this box. Well, let's say the box has dimensions of 2 meter by 2 meters. And if it's three-dimensional, of course, it's 2 meters in depth as well. And so, if this is true, then notice that the top part of the box is at some depth h1, whereas the bottom part of the box is at some depth h2, where h2 is h1 plus an extra 2 meters. That is, this bottom part of the box is 2 meters lower than the top. So if we look at our equation, for the top part of the box, the pressure on the top is the rho times g times h1, and the pressure for the bottom part of the box is rho times g times h2. And so since h2 is an extra 2 meters down, that means the pressure at the bottom of the box is going to be bigger than the pressure at the top of the box. And so if we visualize that, that means the top of the box has a certain amount of pressure. Of course, the sides have a certain amount of pressure by the fluid. And the bottom has a certain amount of pressure. Well, if you look at the sides, this part of the side and this part of the side are at the same depth, so they just cancel. So all the pressure pushing this way to the right is balanced by the amount of pressure pushing to the left, and so obviously if this is a box, it's not going to be moving left and right in the fluid because the pressures are the same. However, we just calculated the fact that the top of the box, P1, is smaller than the pressure at the bottom of the box, P2, and so that means there's a lot more pressure or a lot more force pushing up on the box than there is pushing down. And so what does this do? This basically means that when you have an object placed underwater in a fluid, something like that, it will feel lighter than it truly is. Because if you go to measure its weight, well, its apparent weight is going to be its true weight minus this extra amount of force from the bottom, which doesn't get balanced by the top. And that extra amount of force is called the buoyant force. Buoyant force. So, just looking at a little picture of the box, what are all the forces? Well, you've got mg, gravity, that's the weight of the box. You've got P1, and then you've got P2. And since P2 is bigger than P1, there's a little bit more force pushing up that's not balanced by pushing down. And so the two main forces are the weight, and then a little bit pushing up, which kind of cancels out a little bit of the weight. And so the apparent weight is less than the true weight. That's why when you're in water, you don't feel as heavy, or if you pick something up that's underwater, it doesn't feel as heavy because there's this extra buoyant force which is acting on the object, trying to make the object float. And of course that's important to note, this floating thing. An object floats if the buoyant force is greater than the weight of the object. So, if the object's placed in the water and there's more force pushing up because of the buoyant force than there is force pushing down because of gravity, then obviously the object will float. An object will sink if the buoyant force is less than the weight. And that's why some things sink and some things float. Now, how can you tell if something's going to sink or float? Well, it turns out that if the density of the object is greater than the density of the fluid, the object will sink. So if an object is more dense than water, if you place it in the water, it'll sink. If the object is less dense than the water or the fluid, it'll float. And so that's why boats, for instance, you can have a boat which is extremely heavy, a cruise ship in fact, and it'll float on top of the water, but then you can get, a small rock, a small pebble that doesn't weigh that much, and it sinks. Well, that's telling you that it's not the weight of the object which determines whether something will sink or float, but rather its density. So an object whose density is greater than the fluid you're placing it in will sink, and an object whose density is less than the fluid's density will float. So that's a nice thing to remember. And in fact, there's a little extra thing to note. And this extra thing is something like this. Let's say I have a cup of water and I put some ice in it. Well, if you look at the ice floats, but it doesn't float perfectly. Some of the ice remains in the water and some remains above the water surface. The ice doesn't sink all the way to the bottom, and it doesn't just sit on the top. It actually floats, but some of this ice remains above the water level. And the same goes for a ship. If you have a ship, for instance, or a boat, well, part of the boat will be underneath the water, and some of it will be above. And so if you ever need to find out, let's say, how much of an object will be under the water's surface if you place it in the water or in a fluid, the relationship goes like this. The fraction of the object which is submerged, that is under the water, is equal to the ratio of the density of the object to the density of the fluid. Another way to say it is the volume submerged divided by the total volume of the object is the density of the object over the density of the fluid. So, for instance, if you ask, or if you say, hey, look, this boat, 1/3 of the boat is submerged or under the water's surface, then I can ask, well, okay, well, what's the density of the boat? So you'd say, well, how much of the volume of this boat is submerged? You got 1/3 of the object submerged over the total volume. Let's say the total volume is 1, is equal to the density of the object over the density of the fluid. And if this is water, let's say water has a density of 1,000. So then we could just solve this for rho object, and it turns out the density of our boat would be 1/3 times 1,000, or 333 kilograms per meter cubed. So a nice, easy way to calculate things when you know something about how much of an object is submerged or how much is above the water. Be very careful about the wording, because if I said 1/3 of the boat remains above the water level, then the number you'd place as the volume submerged would be 2/3. It's the other amount of the boat. So just be careful when you're looking at a test question or something. Am I giving you the amount that's submerged, or am I giving you the amount that's above the water level? But this is a nice relationship to know. Now we can move on to Archimedes' principle itself. And so, of course, I will relay the story of Archimedes, or at least what's told. Archimedes was the scientific advisor of a king a long time ago. The king had this very fancy crown, and he started to get a little paranoid about the crown, thinking that this crown that was gifted to him was not actually made of gold, but was a fake. And so he wanted to be sure it was actually gold, so he got his science advisor, Archimedes, in, and he said, I need you to figure out if this is made of gold or not. And so, well, Archimedes went away and tried to think about this. This is kind of a difficult problem because there are substances that look like gold. So how can you figure out if it's gold or one of these fake substances? So he said, well, if I knew the density of the crown, I could compare that density to the density of gold itself. And if they have the same density, then they must be the same material, because gold is gold. It has a certain density, and all gold has that density, of course, if it's as pure as itself and all that. So he said, okay, well, how can I figure out the density of the crown? Well, density, I know, rho, that's the mass over the volume. He said, okay, well, one thing I could do is I can measure the weight, take the weight of the crown, and that would give me mg. So the weight is mg. So if I divide the weight by g, that's the same as the mass. So to calculate the density, I'm going to first measure the weight of the crown and divide it by g, 9.8. That'll give me the m part, and now I need the volume. The problem is this crown, is a kind of weird shape. It's got all these spikes and stuff. And so how do you measure the volume of some really strange shape like this? It's not a perfect sphere, it's not a cube, it's not a pyramid where people can figure out such things. And so he was stumped. How in the world can I figure out the volume of this weird shape? If I could figure it out, then I could calculate the density, and then I'm fine. So the story goes, he was at night thinking about this in the bath, and all of a sudden it came to him. He said, when I get into this bathtub, so here's the tub, let's say, before I get in, the water level is a certain height, but then when I get in, so here's me, here's Archimedes in the bathtub, the water level went from here up a certain amount. So it rose because he got into the bathtub. And what he realized was the reason the water level rose was because it had to make room for his body to get into the bath. And so obviously, the amount the water level rises depends on how big he is when he gets into the bathtub. And so what he said was, the amount of water that's displaced, so the volume of the fluid displaced, and that just means moved out of the way by an object, must be the same as the volume of the object itself, which displaces that fluid. And that makes sense. If you have a cup of water and you put an ice cube in it that's this big, well, that volume of fluid had to move out of the way to make room for that ice cube. So the water level rises a certain amount. How much? Exactly the same as the volume of the ice that you put in. So he figured out the volume of the fluid displaced when he got into the bathtub is the same as his own volume. So he said, what I can do if I want to know the volume of this crown is I could get a container, fill the container with water all the way to the top. Then I could get my crown, put the crown in the water. Then what's going to happen is you're going to have a certain amount of the water leak over the edges. So I'm going to catch that extra water in a container. And then all that water that leaked over the edge, that's the volume, that's the fluid that was displaced by my crown. If I measure the volume of that fluid that leaked over the edges, that must be exactly the same as the volume of the crown itself, because the only reason the fluid leaked over to begin with was to make room for the crown. And so now he has a way to measure the volume of weird-shaped objects. He puts the object in the water level rises, the volume of that rise, how much it rises, tells you the volume of the object. And so famously, he jumped out of the bathtub yelling, "Eureka, I found it," and went on running out the door in his excitement to get the crown and do his little experiment. And so that's what Archimedes is all about. That's what he's famous for, his Eureka moment. So, what does that mean for us? Well, Archimedes' principle, unfortunately, is not just one single thing, but it's kind of a set of different relationships. The first we just found. The first relationship is the volume displaced is the same as the volume of the object. So when you put an object in a fluid, the fluid displaces a certain amount. The amount it displaces is the same as the volume of the object that displaced it. But what else is there? It turns out that another experiment was done, and what this experiment was this volume that was displaced, the volume that leaked over the edges and was caught in this container. They measured the weight of that water. So they knew the volume, of course. They wanted to know how much water is there, what's the weight of this water. And he said, well, it turns out that the weight of the water displaced is exactly the same as the buoyant force on the object that was placed in the water. So, for instance, when he placed his crown in this tub of water here, so all this water leaked over the edges. He grabbed this container, figured out the volume of that fluid, that gave him the volume of the crown. Fine. Second thing that was done was this water that leaked out, they measured its weight. They now know how heavy the water was that leaked out. It was a certain weight. And then they compared it to how heavy did the crown feel when it was in the water. We already talked about at the beginning of this video that when an object is placed in underwater in a fluid, its apparent weight is less than its true weight. It feels lighter, and that's because of the buoyant force acting on the object. So when they measured the weight of the crown under the water and compared it to its true weight, they found the buoyant force acting on the crown was a certain amount, and it just so happens that the buoyant force that acted on the crown is exactly the same as the weight of the water that was displaced by the crown. So that's another good relationship to realize. Not only is the volume of the object the same as the volume of the water displaced, but the weight of the water displaced is also the same as the buoyant force that would act on that object you placed in there. And the final relationship we get from this latest relationship, which is, okay, well, the weight of the water displaced, how can I calculate that? Well, the weight, that's the same as m times g times, well, that's the weight, m times g. But if I don't know the mass of the water, what I'm talking about is density. I know density is mass over volume. So if I want the mass is going to be density times volume. So I could rewrite m times g as rho of the fluid times g times v of the fluid. So the weight of the water displaced is the same as rho times v, that's the mass, times g. So that must be the buoyant force acting on the object. And of course we could rewrite this slightly differently because of the first relationship and say that the buoyant force that would act on an object is the density of the fluid this object is placed in times the volume of the object, because I know the volume of the displaced fluid is the same as the volume of the object from the first relationship, times g. And so here I have my three big relationships for Archimedes' principle. If you place an object in the water, then number one, the volume of the object you placed in that water is the same as the volume of the water that's displaced, that is moved out of the way. Secondly, if you place an object in the water, it will feel lighter because a buoyant force acts on it. How big will this buoyant force be? Well, if you take the water that was displaced and you weigh that water, it's the weight of that water is the same as the buoyant force that acts on the object. And then you say, okay, well, how does that relate to the object itself? It turns out the buoyant force is dependent on the density of the fluid you place the object in, water or oil or honey or whatever, times the volume of the object, times gravity, 9.8. And that, along with the equation weight of an object, the apparent weight, is the true weight minus buoyant force. With these four relationships, you can answer any of the types of questions that you'll see on the homework or the practice problems or the tests. So, like I said, Archimedes' principle, it's not simple in the sense of there's one equation you need to know, this is the equation you use to solve the problem, but rather it's four different relationships. They're all kind of combined together, they all relate to each other, and you use these four relationships on the problems that you'll be working on. Each relationship is very simple. Volume of the object is equal to the volume displaced, and so on. But there's 4 relationships, and you have to worry about all 4 when solving these problems. So that's all I have for this. This should be the end of the theory for the fluids, and we'll move on from here.